Question 32 provides a good example of the way some PE topics are not covered in the NCEES Mechanical Reference Handbook. This handbook will be your only reference material in the exam. Enthalpy wheels are not mentioned in the handbook, yet all the relevant solution data can still be found in it. Initial critical thought solution elements. 1. What are you solving for? Dry bulb temperature of air exiting an enthalpy wheel. 2. What is the fundamental process? Sensible energy recovery by a heat recovery ventilator. 3. What are the first considerations to find the solution in connection to the fundamental process? How to apply the effectiveness ratio properly to the information in the question. 4. Are there key assumptions? Standard air, sea level conditions, no water vapor condensation in the enthalpy wheel, and useless information is contained in the question. This video is brought to you by ExOverZero, which offers the best HVAC PE study material possible. Want to pass the test? Buy the books. Use the link below to purchase. Most of the information in the question and diagram is unimportant. The focus of the question is on the enthalpy wheel, so the variables that matter simply are what's going into it and what's going out of it. Enthalpy wheels are part of a ventilation system for an HVAC design. They transfer energy between stale exhaust airstreams and fresh supply airstreams, while not actually mixing stale air with fresh air. Generally, these systems are called heat recovery ventilators, HRVs, or energy recovery ventilators, ERVs. Notice, if you look up the term enthalpy wheel in the NCEES Mechanical Handbook, you won't find anything. But look up HRV or ERV, and you'll find the information needed to answer the question. It's found in section 9.2.7 and 9.2.8. The difference between an HRV and ERV is an HRV recovers sensible heat, which are dry bulb values, and an ERV recovers both latent heat and sensible heat, which are dry bulb, humidity ratio, and enthalpy values. Remember the heat transfer equations for standard air. The primary thing distinguishing these three equations from each other is what type of heat is being calculated. There's sensible heat, which uses dry bulb temperatures. There's latent heat, which uses humidity ratio. And total heat includes both sensible heat and latent heat by using enthalpy. Total heat is the sum of latent heat and sensible heat. Given the appropriate data, it's reasonable to calculate sensible heat using the total heat equation. That is, total heat minus latent heat equals sensible heat. So the sensible heat equation isn't the only equation that could be used for sensible heat calculations. Following along with these distinctions, it's clear that an enthalpy wheel, by its very name, can recover total heat, and so it can reasonably be considered an ERV. But because total heat contains sensible heat, it can also be considered an HRV. Applying HRV calculations and sensible heat values to a device that could handle total heat values is the first confusing thing about question 32. Another way to put it is this: enthalpy values won't be used when analyzing the enthalpy wheel. The question solves for dry bulb temperature, so use HRV calculations and sensible heat values. For this problem, the biggest step is knowing what exactly enthalpy wheel effectiveness means, and therefore how to apply it. ASHRAE Standard 84 defines effectiveness as a ratio of actual energy transfer to maximum possible energy transfer. So, when the problem states that the enthalpy wheel's effectiveness is 0.8, it's vital to know 80% of what maximum energy transfer. To understand this, compare enthalpy wheels with mixing boxes. Assume all airstreams have the same mass flow, volumetric flow, specific heat, standard properties, and ideal operations, while the only differences are dry bulb temperatures. Here is a mixing box. 2 airstreams enter, 1 airstream exits. Maximum effectiveness and perfect heat transfer for this means the exiting airstream is at 50% of the temperature delta of the 2 entering airstreams. If airstream 1 is 0 degrees and airstream 2 is 100 degrees, then the exiting airstream will be 50 degrees. Think of the concept of 2 things merging together and meeting exactly in the middle. Here is an enthalpy wheel. 2 separate airstreams enter, remain separate, and exit separately. Maximum effectiveness and perfect heat transfer for this means the exiting airstreams are at 100% of the opposing entering airstream's temperature. If airstream 1 enters at 0 degrees and airstream 2 enters at 100 degrees, then airstream 1 will exit at 100 degrees and airstream 2 will exit at 0 degrees. Think of the concept of a temperature U-turn. The actual qualities of stale air and fresh air flow straight, like lanes on a road. But the temperatures of those airstreams do a complete U-turn, never merging or meeting in the middle, just seemingly swapped around. Within the laws of thermodynamics, this may seem impossible. You might think to yourself, as airstream 1 increases from 0 to 100 degrees, and as airstream 2 decreases from 100 to 0 degrees, then they'll both meet at an equilibrium of 50 degrees, similar to the mixing box. But recognize that there are big thermodynamic consequences from 2 structural elements of an enthalpy wheel. 1, both airstreams are held separate from each other. And 2, the mechanical action of a rotating wheel that instantaneously pulls energy in and out of the airstreams. Because the flow of air is powering a spinning wheel, that means an enthalpy wheel can have greater effectiveness than the mixing box, which doesn't convert the mechanical flow of air into anything useful. Now to identify the necessary values to solve. From the diagram, it's clear that a portion of the 6,000 CFM of return air is entering the enthalpy wheel. How many CFM? That's determined by the fact that 1,500 CFM is exhausted from the enthalpy wheel, and 1,500 CFM of outside air flows in. The enthalpy wheel doesn't store air, so what goes in must come out. Assuming standard air conditions means that the same amount of air mass, having the same specific heat, flows in both directions. So outside air at 95 degrees dry bulb flows in from one direction, and return air at 75 degrees dry bulb flows in from the other direction. What the question labels as tempered air is located at this point, 2. The equation for finding the dry bulb temperature at point 2 is found in the NCEES Mechanical Reference Handbook on page 449, roughly in the middle of the page. It's this. Notice how similar this is to a standard mixed air equation, but also notice the key differences. Because it's merging and mixing, this ratio demonstrates one mass flow versus the total of both mass flows. Watch the ExOverZero video on the NCEES Problem 57 for a complete breakdown of air mixing calculations. This ratio depends on which airstream you're solving for. The denominator always matches that airstream. And the ratio is always less than or equal to 1. As stated earlier, there's an equal mass flow of standard air, so this ratio cancels out. The question says the enthalpy wheel is 80% effective. The maximum possible energy transfer is the delta of the entering temperatures. So, 80% of the temperature delta is taken away from the high temperature to give the exiting value. Applying the necessary dry bulb temperature shows point 2 to be 79 degrees Fahrenheit. Option B. To get good at questions like this, You should be able to quickly reference the NCEES Mechanical Reference Handbook to find things like the temperature calculations for HRVs. You can't do that by just reading through it like a novel. Get good at it the only way possible, by practicing lookups in it. To do this, ExOverZero has a one-of-a-kind drill book for the NCEES Mechanical Reference Handbook. Use the link below to purchase.